To break in the vocabulary of hyperbolic functions, why don't we perform some introductory examples? Let's go ahead and evaluate this expression. Now we're going to do this without a calculator. So we're simply going to start with the expression and see if we could substitute. And a substitution for this is hyperbolic sine evaluated at 0 over hyperbolic cosine evaluated at 0. And then we reach back and seek those definitions and make the substitution at 0. And notice we simply get 0. Therefore, the hyperbolic tangent function evaluated at 0 is in fact 0. I'll leave it as an exercise for you to evaluate the hyperbolic sine evaluated at natural log of 4. Make sure you know your log properties, and once again, you're doing this without a calculator. Why don't we look at the derivative of hyperbolic cosine? We're going to try to prove this statement. Now, whenever you're proving an identity, you actually start with one of the expressions. In this case, we're going to start with the expression on the left-hand side. We're going to start with the expression, the derivative of the hyperbolic cosine function of x. Now we're simply going to substitute. And notice this is the derivative of the sum of two functions. And so I'm going to look at each function individually. Let's take the derivative of the first function. That's just 1/2 e to the x. And then we're going to go ahead and add the derivative of the second function, which is e to the opposite of x over 2 with the chain rule. So multiply by the derivative of the inside function, which is simply -1. Now rewriting the algebra, we get a nice pattern. We actually know what this combination of exponential functions are, or I should say is. This is the hyperbolic sine function of x. Why don't we look at another evaluation or another example? Let's evaluate the limit of this function as x goes to infinity. Now, we have to be careful. We're going to use algebra, and if possible, we're going to use limit laws. We're going to start with an expression, and once again, we want to know if we could substitute for that expression. Now we want to get it into the combinations of exponential functions. Then we could actually start checking the form of these fractions. I'm ready to check the form here. If you check the form here, this looks like infinity over infinity, which is indeterminate. So we're going to have to do some manipulation here to make this more friendly. Let's try this manipulation first. We multiply by a clever name of 1. The algebra says it's going to be this. And once again, we want to check its form. This is still infinity over infinity. However, we do know a technique to make a very careful manipulation here. We'll multiply by another fancy name of 1. And remember, with limits, you want to be 2 steps ahead, so we got to check the form again. So the first step ahead is to check the form in the numerator. The form in the numerator is going to be 1 as x gets very large, and the form in the denominator is going to get very close to 1 as x gets very large. Now this is a determinate form. So if you're 2 steps ahead and you find a determinate form, this allows you to write limit laws. And this is the limit law we could write. And finally, we could take the limit, because 1 over 1 is indeed 1. Notice you were able to evaluate this expression without a calculator. Let's look at some more examples. Here's another example that involves working with an expression. Like you did in trigonometry class, you were able to prove lots of identities. So remember how to prove an identity. You must recopy one of the given expressions. Make sure you recopy one of those. I'm going to copy the expression on the left-hand side of the equal sign. And with this expression, you're just trying to make substitutions. And if you look closely, that is in fact e to the positive x plus e to the opposite of x divided by 2, which is just another name for the hyperbolic cosine of x. By the transitive property of equality, we know that the cosine of the opposite of x is indeed the hyperbolic cosine of x. And I meant to say the hyperbolic cosine of opposite of x is indeed the hyperbolic cosine of x. Let's prove another identity. Now remember, when you prove an identity, you must copy one of the original expressions. Notice these expressions are right here. There's one on the left-hand side of the equal sign, and there's an expression on the right-hand side of the equal sign. The expression on the right-hand side looks more complicated, and that's the one I'm going to choose. If it looks more complicated, there's a good chance that I might be able to simplify it. So remember, proving identities is really about simplifying expressions or changing the way the expression looks. So that's a must. You must copy one of the original expressions. Now we use the definitions and substitute. Notice this has nothing to do with angles, has everything to do with exponential functions. We're going to go ahead and multiply the numerators and see what happens. So we get two fractions with a common denominator. You might be seeing a pattern now. If you look at these middle terms right here, and compare them to the middle terms over here, towards the right, you're going to see some like terms that add up to 0. Now the rest of these terms do add up. They add up to 2 of the numerators, and the numerators look like this. All divided by 4. But what's 2 over 4? That's just another name for 1/2. And the magic is now revealing. This final expression is just another name for the hyperbolic cosine of x plus y. We could finally make a conclusion sentence. Therefore, this expression here is indeed equal to the hyperbolic cosine of x plus y. Now, what's an answer to a proof? It's the entire proof itself. So make sure you're able to understand this and be able to prove this statement later on.